Our next application is using calculus, using integrals to find volume. So most of the problems that we're going to do are actually to find the volume of solids, which are solids of revolution. What is a solid of revolution? A solid of revolution is something that you get when you take a curve and revolve it around an axis. So I just looked around my kitchen to find some such things. And what you're really looking for is something that has like a cylindrical symmetry like this. So you can think of, if I took, say I put it like this, right? If I took this curve and I wrapped it around an axis, I might get an object like this. So it's kind of, it's got symmetry of like a circular symmetry. So here's like a little mortar and pestle thing, right? It's got that cylindrical symmetry. Wine bottle is interesting because it has the divot in the bottom, right? So we're going to learn how to deal with that too, because it's like a little hole. You can think of a bead or something that is, or a ring, something like that. I didn't have any beads in my kitchen, so I should have thought, or a vase. You can put the vase along the axis like this, and you can imagine this curve going around and figuring out the vase. And in fact, you can see that I found a cute little GeoGebra applet that actually does that with a vase. So let me show you that. It's kind of cute. Hopefully it'll be working. The other day they weren't working very well, but all of these will be linked in our extra materials if you want to use them. So here's a vase, very similar to my vase. I think my vase is a little fatter, but essentially it's the same thing. It's like the cheap vase that they deliver flowers in. And what you've seen that he has done is he's taken the picture and he's overlaid it with a number of points and taken a polynomial fit for those points. So this is the way it comes. And we'll just right now just see what happens. Come on. So this is the curve in the XY plane like this. So this curve, now this XY plane is now laying down flat. And as we slide around, we're going to turn that curve around that x-axis, and it goes all the way around. So it then maps out that shape. So you see it's not perfect. There's a little bit too much like things here. So what's kind of cute about this applet is that you can, move them around a little bit, make it like you're making it worse here or making it better. Like I'm definitely making it worse. I'm making it look more like my vase than the fat one, right? Let's see if we can make this one even fatter, right? Oops. Okay, that's actually pretty, but that's not what we had to begin with. But anyway, you see how that goes. Now, for the most part, for the problems that we're doing, we will not be, okay, all the way back, right? You'll have a curve like this, and you'll have to imagine in your head what it looks like when we take it all the way around. Imagining it will help you draw the problem out, okay? So how are we supposed, so the next question then is, how are we supposed to use calculus to do this, right? Well, the idea is this. You can, remember what we did before to find areas, we used those rectangles, right? Well, what's going to happen to a rectangle? Here. Let's say this is my vase. Here's my approximating rectangle, right? Here's my delta x, and here's my y. As I move the vase around, this rectangle is going to also move around, and I'm going to end up with a thin disk here, like this. So a thin disk, right? It's a disk. So we know how to find the volume of a disk, right? The volume of a disk is just going to be, it's a small cylinder, right? So it's going to be the area of the circle times the distance here. So it's going to be the area of the circle, which is pi r squared, times the height, but here the height is going to be this delta x, okay? And the radius is actually just going to be the y value. So this was y equals f of x. So the volume, and this is the volume of the small disk. Okay, so then it's going to be pi times y, which is f of x, quantity squared, times delta x. And then we're just going to make a whole bunch of disks and add them up. But really what that means is we're going to integrate. So that's the idea. And let's see, I've got a couple here where you can kind of see that. Hello? It's not working. Oh, there it goes, there it goes. Okay. So this one I had working the other day quite nicely. In this case, they used 2 times the square root of x. So that's this curve. And he chose these two, a equals 1 and b equals 9, right? And he chose 4 disks. So you see, he drew the rectangle, it draws the rectangles. Right, slide me. And it goes, and it kind of goes around. And as it goes around, you see its picture, you can see the picture of those 4 disks. And each of those 4 disks, you can figure out the delta x and the radius, which is going to be f of x, is going to be given by that point, right? Now, as you can see, if I increase the number of rectangles, then of course I'm going to increase the number of disks, and it's going to get, just like with area, it's going to get closer and closer and closer to an approximation of the correct thing, right? So here, the way it's drawn n equals 50, you can see exactly that it's almost like what you'd expect, like this bowl-shaped thing, okay? It's not really a bowl because it's solid, right? We have that whole solid bit, but nevertheless, taking 50 rectangles, and then what we're actually going to do, of course, is take the integral. So we can take the integral and see how that goes. If we can go back to that. In fact, we can just do this problem. Okay, and in fact, in this particular applet, this was working quite nicely. You can change the function, you can change these parameters, you can change the number of differential rectangles it's showing. But maybe you just want to find out how are we going to use an integral to do this problem. So I'll do it really quickly here. Okay. So there. Let me make it bigger now. Stop share. So our function was that from x equals 1 to x equals 9. And what we had said was that the volume was going to be the limit as n goes to infinity of the sum I equals 1 to n of all of those disks. So that would be pi times the radius squared delta x, right? So once that's a Riemann sum, but of course I want to take the integral. So what is this going to be then? It is going to be the integral of pi f of x squared dx, and my x went from 1 to 9. So all I have to do, this is my function f of x in the picture. There. All I have to do is shove that in there and do it. It's not a hard integral, right? Because I've got 1 to 9, I can pull out the pi. I've got 2 root x squared dx. So I have, this is going to be 4, right? Pi 1 to 9 of 4x dx. So I end up with 2 pi x squared from 1 to 9. And so what is that? 80. Yeah, right. Why did you, oh, it was probably a big, right? It was, they chose 9. I don't know. Why is it 9? So like 81, what's 81 times 2 is 100. It's not 198, it's 162. So 162 pi minus 2 pi, so we get 160 pi. I'm sorry if you can't see that, it's too small. But anyway, you can figure that out. Okay, so we're able to then get the exact answer quite easily once we've got this set up. Now let me show you one more. Oh, I have to share the screen again. Sorry, guys. This one was nice because it showed the disks nicely. And you can actually, as I said, you can change this. I just didn't do it today. But that one was working for me nicely. Now this one isn't even loading. Come on. All right, well, if it's not loading, it's not gonna work. So maybe I will just do a separate one for that, a separate video, if you guys wanna look at that. Come on. Anyway, it's still linked if you want to play with it, but I guess GeoGebra isn't working very well now. Okay, well, we'll go back to that another time.